And now, without any further delay, I would like to turn today's event over to Marcella Wolf with ATIS. Marcella, you now have the floor.
Thank you, Kristen. Hello, I'm Marcella Wolf with ATIS, and I'd like to welcome you to today's webinar. Precision Timing Protocol, or PTP, is a vital enabler for new networks and features within many industries, including mobile communications, power, finance, broadcast, industrial automation, scientific research, and more. With its ability to achieve clock accuracy in the sub-microsecond range, PTP is an essential force in today's measurement and control systems. And innovations are being made now to prepare this protocol for the future. In today's webinar, our experts will discuss the basics and future developments of precision timing protocols. Now, without further delay, I'm delighted to introduce today's moderator, Silvana Rodriguez. Silvana is the Director of System Engineering for IDT. Silvana is the Secretary for the IEEE 1588 Working Group and the editor of several ITUT recommendations. And now, Silvana, the floor is yours.
Thank you very much. Good morning, everyone. I would like to introduce our presenters for today. They are Tim Frost. He's the Strategic Marketing Manager for Calnex. He has several years of experience in next-generation synchronization techniques, having worked with both symmetrical and Starlink semiconductor on packet synchronization technologies. He has been active in the ITUT Network Synchronization Experts Group, Q13, Study Group 15, the small cell forum, where he was the editor for their synchronization white paper, and also in the Metro Ethernet forum, where he was the editor for their circuit emulation standards. Our second presenter is Pat Diamond. He's the founder and principal of Pat Diamond Consulting, which focuses on synchronization technology and techniques for telecommunications, industrial and financial networks. Pat is an early pioneer and evangelist of 1588 packet time technology starting in 2003. Pat is currently the co-chair of the upkeep subcommittee of the 1588 working group. Tim and Pat, thank you for joining us today. So now I would like just to go to, I just like to talk about what is behind this use of 1588 on the network. So really here I'm focusing on the mobile network. So I want to emphasize the exponential growth of bandwidth in mobile data traffic due to use of devices such as smartphones and tablets. With the growth in bandwidth, service providers are moving to Ethernet due to scalability and economics. With the use of Ethernet, then there is a need of transport and synchronization through synchronous network, and therefore the use of IEEE 1588 and synchronous Ethernet for network synchronization are becoming prominent. On this slide, this is a table that comes from an ITU document that's called G.8271. These recommendations deal with time and phase synchronization aspects of packet networks. It does give you an idea of the level of accuracy that we are looking forward to in terms of recovering synchronization from the network. ITU is defining several recommendations for phase and time synchronization that will focus on targeting accuracy better than 1.5 microseconds. That's class 4, 5, and 6 on this table. These recommendations include synchronous Ethernet and profiles for 1588, also known as PTP for Precision Time Protocol. This webinar will focus on Precision Time Protocol fundamentals and features. And at this time, I would like to ask Tim to begin our presentation.
Thank you, Silvana, and good morning, everybody. So, first of all, I'd like to go back to how the conventional timing signals work. If we look at a conventional timing signal, like a frequency signal, it's defined as a nominally periodic signal generated by a clock. And you can see here we have a digital timing signal. And you'll notice that it has regularly repeating features here, which are the edges of the signal, and these are called significant instants. And in a timing frequency signal, those significant instants are equally spaced. So of course in real signals, that's not quite true, and there's always some timing jitter and wander as those edges move about in time. But the nominal or the mean spacing between those edges gives us the frequency. Now, a packet timing signal could also be thought of as a nominally periodic signal generated by a packet slot. So if we look at a train of packets here, we have 4 packets moving along a network, and this packet timing signal too has significant instants in exactly the same way as a conventional timing signal. And you'll notice here that it's not the content of the packets that are important, it's actually the position in time. And the spacing of those packets should be periodic, and the spacing should be regular. But of course in packet networks there's also some impairment, and we call that packet delay variation. And as the delay through the network varies in time, that will cause some noise on the frequency content of that signal. Now, of course, not all packet timing signals are periodic, and the way we manage that is through the use of timestamps. So if you imagine a new packet timing signal, this time with timestamps, as a sequence of timed events generated by a packet master slot. So you see here, I have a train of packets again, and these packets now contain timestamps. We still have significant instants. So we still have the position in time of the packet as the most important thing here. But because of the timestamps, we don't now have to be regularly spaced. And we can use those timestamps to reconstruct the original frequency. So if you see here, the first packet contains a timestamp of 1. The second packet contains a timestamp of 4. So we can reconstruct the frequency as the spacing between those 2 packets divided by the difference in timestamp. And you can see therefore that we can reconstruct the frequency, and the gap between the second and the third packet is now 4, so there's a larger number of periods between those 2 packets. So the use of timestamps enables us to reconstruct a frequency even when we're now arbitrarily spaced. But it's still the position in time that's important. Now then, so how do we synchronize in time as well as the frequency? Well, PTP, Precision Time Protocol, uses a 2-way exchange of timed event messages. So this is the PTP protocol. We have a sync message which contains a timestamp, and that arrives at the clock, at a slave clock at a time T2. So now we have 2 timestamps, T1 and T2. The second message we have is what we call a follow-up message. If required, it may be required that the master send this follow-up message to tell the slave what the accurate value of T1 actually is. Now, some packet blocks are able to embed an accurate timestamp in the message itself. Others need to send a subsequent message to tell you what that accurate timestamp is. So the event message, the critical message, is a sync message. The second critical message or event message is a delay request message, and that leaves clock at time T3, arrives at the master clock at time T4. The master clock then sends a fourth message type, the delay response message, to send the value of T4 back to the slave. Now we can obtain the slave frequency by comparison of timestamps over multiple messages. For example, if the slave clock T2 time is accumulating faster than T1, we know that the slave clock frequency is too high and it needs to be adjusted. Well, we can lock the slave frequency just by looking at a single message or a single set of messages. But to get the time, we need to do a little bit more. We need the round trip delay. So what we do is we take T1, T2, T3, and T4, and we can calculate the round trip delay. And then we estimate the one-way delay, the delay from the master to the slave, as half of that round trip delay. So we end up with this equation here, which is the T offset, the offset between the slave clock time and the master time. So you notice that that assumes symmetrical delays. It assumes that the forward delay equals the reverse delay. And if that's not true, then we have a time error. And that's equal to the difference between the forward and reverse delays, the delay of the sync message and the delay request message, divided by 2. And that's something we need to remember with PTP clocks. Now then, there are a number of impairments that we can have with this kind of packet system. If you imagine a master clock sending a packet to a slave clock, you see here, it leaves the master clock, it goes down to the protocol stack, it goes through a number of network elements in the network itself, and each of those network elements may have queues within them. For example, if it's a switch or a router, there may be receive queues and transmit queues, and all of those queues add delays to the packet. And finally, it comes to the slave clock, and it goes back up through the protocol stack up to the PTP layer of the slave clock. Now, one thing that PTP does, Precision Time Protocol, is that it timestamps the packet at the physical layer. And that physical layer timestamping means that we can remove the delay that occurs as the packet passes through the protocol stack. And that's quite important because the protocol stack delays can be quite long as it goes from the PTP layer to the UDP layer and then up into the IP layer and the Ethernet layer. So timestamping at the physical level tells us the actual time that the packet left the clock and not the time that it was actually generated in the PTP layer. So it allows us to eliminate the protocol stack delay from the delays of the packet. And similarly, we can do the same at the slave clock. We can timestamp the packet as it comes in and then send that information to the PTP layer of the slave clock.
Kim, before you move on to the next slide, I got a question for you. What about all the PDV accumulated as the packet travels through all those queues in the network? How does PTP handle that?
Thank you, Savannah. So PTP has a couple of ways that it can handle the queuing delays through the network. So the first of these is what we call a boundary clock. Now, a boundary clock is a switch or router that contains an embedded PTP slave and a PTP master. So the messages or the packets come into the boundary clock, switch or router, and ordinary messages are just passed through the switching function and come out on the output ports of the boundary clock. PTP messages are forwarded up to the PTP slave port in the boundary clock. And the timing of those messages is recovered and used to synchronize the local clock within the device. This local clock then is used to generate new messages that go back out of the boundary clock and onto the next clock in the chain. Now, the purpose of that is that it removes the delays through the switching and queuing elements of the switch of a router from the PTP path, because we can use hardware timestamping again to timestamp the messages right at the physical layer as the messages come into the device, and also timestamp them on the way out right at the physical layer again. And then the boundary clock terminates that traffic and regenerates it. So the switching and queuing delays through that device are eliminated from the PTP path. And that's an important principle that's used in PTP systems to try and eliminate the queuing delay. Another method which is also incorporated in PTP is what we call transparent locks. And there's two types of transparent locks in PTP. There's what we call end-to-end transparent locks, and end-to-end transparent locks take a slightly different approach to boundary locks. What they do is we timestamp it in the physical layer again, so the PTP messages come into the switch or router that contains the transparent lock. They're timestamped as they come in, and then that time of arrival is sent up to what we call a residence time bridge. And the residence time bridge takes note of the time of arrival, and then as the PTP messages pass out of the device again, it takes note of the departure time. And from that, it can calculate how long did the packet spend within the switching and queuing elements in that switch or router. That time is what we call the residence time. And the transparent lock uses that residence time and adds it to a correction field in the PTP message itself. So by the time you get to the end of the path, the correction field contains the sum of all the residence times in each transparent lock as it's gone through the network. And that means that the PTP slave clock knows how long the packet took to get there. And that's an important factor for it to know, so that it can eliminate that from its calculation of the frequency or the time that's coming from the original master clock. The second type of transparent clock is defined in IEEE 1588, and that's what we call the peer-to-peer transparent lock. So what peer-to-peer transparent locks do is they have an additional function, as well as the residence time calculated from, say, the PTP sync messages flowing through the device. The residence time bridge also exchange what we call peer-to-peer messages with the next hop, either to its left or its right. So you can see here the transparent lock, and that communicates with its neighbours. And what those peer-to-peer messages do is they measure the delay from the previous hop to the current switch, and also to the next hop. So that delay is the delay through the wire itself or through the fibre. So by the time you now get to the PTP slave, you've now got the full delay, including the fibre delays or the cable delays, from the PTP master to the PTP slave. That full delay is incorporated into the correction field. And for that reason, we no longer require the delay request or delay response messages, because the full delay is incorporated into this correction field now, including the link delays. So that's a second type of transparent lock.
Tim, before you move on, I got another question. How does PTP handle a large network of clocks? For instance, there may be many thousands of slave clocks out there, with a complex network of boundary clocks and transparent clocks in between.
Yeah, thank you, Solana. But the organization of PTP networks, as you say, it can be quite complex, because there are thousands of clocks out there. Even if there aren't very many Grand Masters in the network that are actually generating packets, there are a large number of slaves, and then if you include boundary clocks and transparent clocks, there are hundreds or thousands of clocks out there. Now, the way that PTP handles this is a process we call the best master clock algorithm. And the best master clock algorithm is basically how PTP clocks organize themselves to optimize the sync quality. So all the clocks that are capable of being master clocks in a PTP system exchange messages between themselves. And basically those messages contain the quality level or the quality of their source of timing. And in the process of exchanging those messages, they elect the clock with the best source of timing to be what we call a grand master clock, or the source of timing for that particular network. So when the BMTA is finished, there's a single source of timing for the entire clock domain. The BMTA also works to prevent timing loops. So you don't get a PTP clock synchronizing to another clock, which is synchronized in turn back to itself again. Those timing loops are eliminated by the BMTA. And the other main job of a BMTA is to reconfigure the timing hierarchy in the event of a failure. So, for example, if the grand master clock goes down, or if some of the boundary clocks go down, the BMTA will reconfigure to ensure that there's always a valid route for timing within the system.
Okay, I get another question here, Tim, before you move on. PTP is a complex protocol with multiple options and functions. How do I know what to implement for a given application?
Thank you, Silvana. You're right, PTP is a complex protocol, and it's been designed for many particular applications. And the way that it manages this is by the use of what we call profiles. So there are many different features in PTP, and they're not all used by every particular application. So PTP profiles are defined by other standards bodies, not necessarily IEEE themselves, to tailor PTP to a particular application. And a profile will define a combination of options and features and attribute value that are used within that particular application. So, for example, it facilitates interoperability between equipment designed for that purpose, because that equipment is designed to use a subset of PTP features required for a particular purpose, or not have to use a whole protocol, then some of those features may not be relevant. So some of the examples of profile that have been defined, there's IEEE 802.1AS, which has been defined for time-sensitive applications like audio and video. There's IEEE C37.238, which has been defined for power system applications, for example, used in power stations. And then there's IEEE G.8265.1, and that's been designed for using PTP to distribute frequency synchronization to cellular base stations. And a number of other profiles that are in development by ITC and IEEE, and SMPTE as well. And there may be some others that I don't know about. But profiles are very useful tools that tailor the features and options within PTP to particular applications.
Thank you, Tim.
Thank you.
Sorry, I interrupted you.
Yes.
Thank you very much,
Okay.
Tim.
Thank you.
Sorry, I'll let you speak.
So that's the end of my talk, and if you want to know more, then you can ask questions or come along to the WSTS conference in June.
Thank you. Thank you very much, Tim. And with that, I'll pass it on to Pat Diamond. So that's going to be our next part of the presentation. Pat is the founder and principal for Pat Diamond Consulting. Please, Pat.
Good day, everyone. Thank you for joining us. I hope we're going to answer some of your questions and look forward to any questions you might want to ask. IEEE 1588 has two permutations. One is 1588-2002. The other is 1588-2008. And that's the modifications that are what I'm going to address today. The IEEE has a system that they call PARS, which is a project action request. It's approved by an organization called Nescom, which basically authorizes the creation of a working group from a study group to either produce a new standard or produce an update or amendment to an existing standard. They also have some rules that every 5 or 10 years an existing standard needs to be modified, updated, or what's called deprecated, which means removed. So for 1588-2008, there are several issues in it that over time have become problematic and are in need of modification. Some of those include message paths, timestamp point issues, and layer violations. So the PAR was created, and as you can see here on this slide, these are the functions or objectives that the PAR has laid out for the working group to correct. The evolution of this standard is kind of interesting. There's a lot of things that people want. For example, TAAS, or Timing as a Service, is something that telecom operators are being asked for by industries that use their networks, some of which are mobile wireless, some of which are audio video, some of which are industrial, some of which are scientific, some of which are financial. And those industries are not with a core competence for timing distribution systems. So they would like to get timing from the telecom networks who do have that core competence. And that's a challenge that those folks face. And 1588 could be a mechanism for which they deliver the timing to these industries, with a plus or minus 500 nanosecond accuracy is the current goal. Financial marketplaces such as high-frequency trading are one of the largest consumers of timestamps or timing in any industry. And right now they have a requirement for timestamp accuracy of under 10 microseconds. And that's very, very difficult to achieve. But when you consider there are billions of transactions that occur a day, they need the timestamp accuracy to authenticate and validate that the trades are being done according to the set of rules. High accuracy physics, such as the Large Hadron Collider in CERN, Switzerland, requires timestamp accuracy at sub-nanosecond levels. Particles traveling at the speed of light require timestamp precision that is, until fairly recently, unachievable. CERN and the engineers there have produced a mechanism whereby they can do timestamps with a standard deviation of approximately 59 picoseconds. However, they're doing it in a mechanism that they created, and that mechanism and mechanisms similar to it are being considered for the next generation of 1588. Security and management capabilities for the standard need to be improved. Those were not afterthoughts, but they weren't highly desirous by the community that created the 1588-2008 standard, because it wasn't really understood at the time what could we do with this or how would it be adopted. So that's another one of the issues that the working group is struggling with. And obviously we have to be backward compatible, because this is a multi-billion-dollar industry and there are millions of clocks already deployed. And whatever it is that we do with a new standard is going to have to work as best as possible with clocks from the old standard.
Pat, before
yes.
you move on, I got two questions for you. The first one is, how were the issues in 1588-2008 needing resolution identified and communicated to the IEEE?
The IEEE used to have an organization that did what was called interpretations. And interpretations was a group of folks that excuse me, were part of the original committee that would receive requests and input from the user community. And that was one way in which information and questions and so on were compiled in lists of issues that needed to be addressed. And some of the others are just industry feedback from a lot of folks that are desirous of being able to use the standard, but wanted features that it didn't have. So those were all put into lists, or when the new study group was formed last year, these people attended meetings and asked questions.
And the other question I have is that are the market industry identified on your previous slide represented on the PTP Networks working group?
They are, which is really kind of cool. When we did the 2008 standard, the distribution of people that were participating in the working group was heavily skewed toward telecom. This particular working group has quite a large distribution across all the industries. So they're very well represented, and it's very interesting to see them interplay.
Thank you.
Sure. The working group is organized as any other IEEE working group. There's a chair, a vice chair, secretary, editor, an INM Society sponsor. That's from NIST, Instrument and Measurement Society. That is there as a sponsor representing NIST, who oversees the activities of this organization. There's a public website, and the link is listed here. You can go onto that website and look and see what's going on. There's a lot of things that are hidden because the IEEE does not allow us to, for example, publish drafts or to have discussions about standard-based activities placed in the public domain. But there's a lot of information at that website that one that's interested can use to see what's going on. The task force this time, unlike last time, is actually organized into subcommittees. And each subcommittee has a specific challenge and goals, and we'll get into those. But the subcommittees are upkeep, architecture, security, high accuracy, and maintenance. The architecture subcommittee has a set of charters and objectives, and they're articulated here. They have requirements for defining ports, time counters, and clocks. Ports are hierarchical in the 1588 community. A port can be a physical event, a physical location. It can also be a logical component of a physical element. Clocks and the relationships between them and the ports are something that have to be improved in their definition. Network layers. This is an issue where, for example, in 2008, the transparent clock, in the way that it was suggested that it be operating, although it's not mandated, actually violated the 802.1q standard. So that's got to be fixed, and that's in here. Mappings. This is what Tim was talking about to some degree about profiles and how to map the standard and the protocol across different network environments. The profiles themselves, and how can they interplay, and how can they interact, and how do we create a set of profiles, for example, that can share a common network instead of having to have a separate network for each profile. How to make endpoints or clocks that use a particular profile be able to communicate amongst each other to tell each other what profile it is they use. Those things that are being discussed in architecture. And general requirements, which is just things that are not highly specific that may come up in the process that we need to work on. High accuracy is looking at ways to enable the standard to actually deliver sub-nanosecond time. That's basically what it does. And there's ways to get there. And they're all articulated here. I don't need to read them all to you. But they're looking at things like what's called White Rabbit, which is the name of the mechanism used by CERN and the Large Hadron Collider to produce the extremely precise times that they do. So there's a lot of activity in this group by each one of the industries, surprisingly. And there's some very interesting work being done in there. Upkeep. Upkeep's job is twofold. One is to fix the warts that existed on the 2008 standard, to clarify ambiguous language, to such as language that was raised through the interpretations group over the past few years, to restate how things need to be, such as the acceptable master table issues, such as the layer violations that the transparent clocks inadvertently were carrying out, those sorts of things, and there's quite a large number of them that have to be incorporated into the new document, which may or may not be a new standard. It may just be an amendment to 2008, or it may be an entirely new version. That hasn't been defined yet. Once that is done, and hopefully that'll be done by the end of this year, the role of ensuring interoperability falls onto this community. Because there are different subcommittees, and each one has a defined set of challenges and tasks, it's very important to make sure that there isn't an inadvertent creation of non-backward compatibility or incompatibility. So this subcommittee will be responsible for making sure that, that none of those events take place. Management. This is a very important one in that we're trying to build mechanisms for SNMP and native management protocols and OAM mechanisms to control, manage, and interrogate 1588 clocks of all kinds in all profiles, and to bring them into a common set of understood syntax so that a network management system could conceivably manage many different profiles of 1588 protocol deployed across common networks. So this is a very interesting community, and again, all of the industries are represented very well here. And the last one, and certainly not the least one, is security. Security by itself is difficult enough, but when you're trying to add security to packets that by themselves have to have a high level of determinism as they propagate through networks, is not an insignificant challenge. And we've got some of the industry's best experts, most knowledgeable folks working on how to do these things, how to define them. Now, security will be optional. It's not going to be a requirement for 1588 conformance, but there are several industries that have expressed an interest in making sure that timestamps are protected and event messages are protected and so on. So we're trying to figure out how to do that in the security subcommittee. What else are we going to work on? Yes.
But before you move on, I got 3 questions I think would be nice to address now instead of leaving to the very end.
Sure.
The first one is how the efforts of these subcommittees be integrated into a new standard document.
Okay. That's a very good question. One of the functions of the working group officers is somebody is the editor, and that individual has the responsibility of taking recommendations that come from a subcommittee that go to the working group plenary and are voted on to be included in the new document. Once that vote is done and the statistical compilations of the votes achieve the IEEE rules for acceptance, that information is forwarded on to the editor and say, add this to the standard. So it's a very incremental process, but it's very rigorous, and everybody on the working group that has voting rights participates.
And how this standard will be ratified and approved for publication?
There's 2 steps there. First, you have what's called a working group ballot, and as the subcommittee activities are integrated into the new draft is then completed to a point, and that new draft is then sent to the working group members for comment and voting. You can vote approve, disapprove, or abstain. And within the approve or disapprove, there's categories of why. Is it a technical issue? Is it a grammar issue? What is it? Those answers or comments, if you will, are collected electronically. They go to the editor of the document, who then communicates through plenary meetings, which we hold on the phone every month, to go through each one of the questions and comments and find a way to mitigate it. Once it's mitigated, that new document, new text, is reconstructed and the document is put out again for working group ballot. Once working group ballot passes the statistical requirements for IEEE, it goes to what's called sponsor ballot. And sponsor ballot is any voting member of the IEEE 1588 standards organization that wants to vote on this is given the privilege of voting yes or no, and it goes through a very similar process. So it's highly rigorous and highly organized, but that's how all IEEE standards are done.
And one more question, and would the public website have a copy of the new standard work in progress?
No. The IEEE does not allow us to publicize drafts, and the reason is really pretty simple. We do not want individuals or companies or industries taking a draft document and going off and building product against that document only to have it changed later. So the draft documents are very, very carefully controlled within the voting members of the working group, and not until a draft is ratified is it allowed to be brought out to the public.
Okay, thank you.
You're welcome. So what other things are being done? The best master clock algorithm has got some issues that have to be sorted out. We've got to improve deployment and implementation guidelines. We're getting operator views, wireless operators, industrial operators, professional audio, finance, scientific, we're getting improvements from them. Test and measurement, we're learning a lot of things from them. GNSS vulnerability is a big deal, and how 1588 could possibly be used as a backup for that. That's under discussion. We're working with a lot of different ITU standard groups, the IEEE standard groups. There are liaisons going back and forth between P1588 working group and several of the other standards organizations. So the goal of this process here is to produce a standard that is well understood and accepted by many of the adjacent standard development organizations that have adopted it in some way, shape, or form. And of course, security is a big issue. And there are other things that we don't know about yet that will come up over the next year or two as we go through it. If you want to know more, come to WSTS in June. It's a great conference. It addresses these issues in high detail. All the experts in the world that have anything to do with this, they are there. So I couldn't encourage you more to come and attend that workshop. It's in San Jose this year. Thank you very much.
Thank you, Pat. So at this point, there are still a few questions that has not been addressed during the presentation, and I would like to thank you all who have submitted the questions online. So there are two questions that are for Tim. The first one is, how does NTP is different from PTP? NTP also exchange some messages and use an offset to calculate the delay.
Yeah, so thank you for the question. NTP and PTP basically use the same principle when calculating the offset. So they both use an exchange of timed messages. So in that respect, they're using the same principle of sending a message in each direction, calculating the round-trip delay, and using that to estimate the offset of the stage clock. What PTP does that's different to NTP is that it uses hardware timestamping, which we've discussed in the presentation. So that eliminates the protocol step from the equation. And it also uses this concept of boundary clocks and transparent clocks. Now, NTP has something similar to boundary clocks in that you can use a chain of blocks in NTP. If your computer tries to synchronize to an NTP master, then that NTP master is probably synchronized to another NTP master somewhere else, back to the ultimate source of timing. So that, in a sense, is similar to boundary clocks. But PTP's main difference and the main reason why it's more accurate is this concept of hardware timestamping.
Thank you, Tim. The other question is also for you, and it was related in between master enclaves. They can be miles apart. And if so, is this where the 1.5 microsecond phase requirement must be met?
Thank you, Savannah. So yes, that's very true. The master enclave can be many miles apart. This is something that the ITU was working on at the moment. 1.5 microsecond is required to synchronize cellular base stations for example, the time division duplexing system that's used probably primarily in China at this point in time, but also some of the other LTE features will require very accurate time and phase requirements. So the way the ITU profile that's about to be completed achieves this, is to use bounded blocks with every node in the network. So every node in the network must contain a bounded block in order to remove the switching and routing delays from the PTP path. And it turns out that actually the noise accumulation through that type of network, operating over Ethernet and with bounded blocks at every node, the noise accumulation is not very high. But the main issue is actually in terms of the links themselves, and that the fibers of the forward and reverse directions, so the upstream and downstream directions, may be physically different, and that may cause a difference in delay, which can add up over the course of many kilometers of fiber. So that's what we call an asymmetry, and it causes a time error. Remember the equation that I presented. That equation relies on the fact that the delays are equal in both directions, and that's the biggest problem with PTP. And actually, that can't be solved by PTP itself. It has to be solved externally by some other means to calculate what the asymmetry is and then use that to compensate. I'm sure that's the subject of many talks at WSTS if you want to come along and find out more about it.
Thank you, Tim. I have a question for Pat now. How the work on the current work on 1588 would affect the 2008 version of IEEE 1588? There are many deployments out there today using the version 2. So how this would be affected by the new version?
That is the fundamental question that the new working group has, and part of the PAR charter is to maintain backward compatibility between this new work and the existing deployments. There are undoubtedly going to be a few things that aren't backwards compatible. For example, the work that's done in high accuracy will more than likely include functionality that didn't exist when 2008 was done. May very well be the case in security. And it's possible there will be some components of the architecture discussions that would be incompatible because they're new, not because we create an incompatibility. Those functional characteristics, for example, the acceptable master table and BMCA that are being addressed, the backwards compatibility component of that activity is paramount in the working group. So those things that exist in 2008 today will be maintained as backward compatibility if it is technically and humanly possible. Those new features that are added in the new function may or may not work with 1588-2008. And part of the requirements of the working group is to articulate very clearly in the standard for each one of those subclauses where there is an incompatibility, that there is that incompatibility. So that's what we're going to do.
Thank you, Pat. Tim, another question for you. What are the most critical constraints in network design for PTP?
Yeah, thank you. So I would say the most critical constraints in network design are in terms of how much error can be introduced by each component. So, for example, I mentioned a minute ago the asymmetry issue with link delays. Another place where asymmetry can creep into this is in the nodes themselves. In the ITU profile, each node is allowed to introduce up to 50 nanoseconds of constant time error or offset. Now that 50 nanoseconds, although we're timestamping at the physical layer or as close to the physical layer as we can get, there are sometimes delays within the PHYs themselves, within the physical layer components, that mean it's very difficult to get that completely accurate. So that 50 nanoseconds is to allow for any inaccuracies in that process. But if you have a network with a large number of boundary blocks chained together, for example, then 50 nanoseconds per node very quickly builds up into a sizable error. So, for example, the current profile recommends no more than 10 nodes in a chain because of that build-up of error just at the physical layer of the device. And that's probably the most critical constraint. We agreed at the last meeting actually to reduce that 50 to 20 nanoseconds. So that's actually quite a hard target to meet. So whether there's any equipment out there that meets the new 20 nanoseconds standard is another question.
Thank you, Tim. Another question is hardware clock. It's also for you, Tim. Hardware clock needed for PTP should be in place at the physical layer. That means we need to modify the physical layer of the device?
That's correct. These aren't standard switches and routers anymore. These are switches and routers with a PTP boundary block or indeed a PTP transparent block built in, which means the physical layer does need to be modified. Now, if you're building a greenfield network, that's not an issue for you. If you're trying to operate PTP over an existing network, then that is indeed an issue. And the ITU are about to commence work on a new profile that will allow PTP to be operated over conventional existing switches and routers that aren't aware or aren't what we call PTP aware. So the physical layer has not been modified. You will get a build-up of packet delay variation as you go through those. And studying that noise accumulation and working out how many switches and routers you can go through before the sort of noise accumulation through the increase of packet delay variation, before that becomes too excessive to be able to recover good timing. That's part of the study that's now going on within ITU itself.
Thank you, Tim. I would like to thank everyone who have submitted questions. Those of you who have that we didn't have a chance to answer the questions, we'll get back to you after the webinar. Thank you very much.
Unfortunately, we've run out of time, and I'd like to thank everyone for joining us today. On behalf of ATIS, thanks again for attending today's webinar, and please enjoy the rest of your day.
And thank you so much. And to all of our presenters, thank you. And ladies and gentlemen, that does conclude today's live meeting. Thank you so much for joining us today. You may go ahead and disconnect your phone line now.